Before we start, we need a little bit of information about what a vertical asymptote is. Vertical asymptotes appear in rational equations when the left side of the graph and the right side of the graph approach y values that are either reaching towards positive infinity or negative infinity without bounds. Vertical asymptotes act as a wall to the graph. They are always parallel to the y-axis. They also set a type of domain restriction because the graph is undefined at this x value. Sometimes we can have many vertical asymptotes. Vertical asymptotes can never be crossed. They will always be written as equations because vertical asymptotes extend up and down, thus representing vertical lines. Since they represent vertical lines, you must write vertical asymptotes as an equation, like x equals, and then the number. If you do not represent it with an equation, it will be considered wrong. We're going to go ahead and start with example 1, where we have g of x is equal to 1 divided by x squared plus 3x plus 2. We need to find out where our vertical asymptotes are. The mathematical procedure to figure out where our vertical asymptotes are is to factor our numerators and to factor our denominator to simplify our rational expression. So I end up with g of x is equal to 1 all over. I'm going to factor my denominator using MIFTER. I end up with the factors x plus 2 and x plus 1. After I make sure no factors cancel, I'm going to go ahead and set my factors equal to 0. My first factor is an x plus 2. If I set it equal to 0 and solve for x, I end up with x equals a negative 2. I can see on my graph that my graph approaches my negative 2, but it never crosses it. It starts extending up, never crossing it, and it goes down all the way towards negative infinity, but it never crosses that negative 2. Then I can look at my second factor. I have an x plus 1. If I set it equal to 0 and solve for x, I end up with x is equal to a negative 1. My graph extends up and it extends down towards negative infinity, but never crossing the negative 1. Let's see why this happens. If I were to use these values back in my original problem, I would have g of negative 2 is equal to, and I would plug in this negative 2 into my original problem. So I would have 1 all over parentheses negative 2 close parentheses squared plus 3 times a negative 2 close parentheses plus 2. If I were to simplify this, I would end up with 1 all over negative 2 squared gives me a 4. 3 times a negative 2 gives me a negative 6 plus 2. I would simplify some more. I would end up with 1 all over 4 minus 6 gives me a negative 2. Negative 2 plus 2 gives me 0. This is considered undefined. Let's see what would happen if I were to plug in my negative 1. If I had g of negative 1 is equal to 1 all over parentheses negative 1 close parentheses squared plus 3 times a negative 1 plus 2, and I were to simplify it, I would get 1 all over negative 1 squared gives me a 1. 3 times negative 1 gives me a negative 3 plus 2. I would end up with 1 all over 1 minus 3 gives me negative 2. Negative 2 plus 2 gives me 0. And I would get another value that would be considered undefined. That means I would not be able to use a negative 2 or a negative 1 in my problem because everywhere they occur, it will give us an undefined value. I can get really, really close to those values, but I can never use those actual values. And that's what causes our graph to increase towards positive infinity or to decrease towards negative infinity. Because the closer we get to either the negative 2 or the negative 1, it causes us to get really, really large y values, or it causes us to get really, really small y values. Let's take a look at example 2. If I wanted to find out where my vertical asymptote was occurring, I would factor my numerators and factor my denominators. I would end up with f of x is equal to x plus 1 all over x plus 1, x plus 2. Then I would look and see that my x plus 1 in my numerator and the x plus 1 in my denominator are the exact same factors. So if I were to reduce this, I would end up with 1 over x plus 2. In order to figure out where your vertical asymptote is, you get the factor that remains in the denominator, not the one you canceled, but the one that remains, and you set it equal to 0. So I would get x plus 2 equal to 0, and I would solve for x. So x equals negative 2 is the vertical line going through where x is a negative 2. This is where our vertical asymptote occurs. It extends all the way towards positive infinity and all the way towards negative infinity. Let's take a look at example 3. On example 3, I have f of x is equal to x squared plus 5x plus 6, all divided by x squared plus x minus 2. If I want to find out where my vertical asymptote is, I'm going to factor my numerator and factor my denominator and simplify. I end up with f of x is equal to x plus 2, x plus 3, all over x plus 2, x minus 1. I cancel the factors they have in common, and I end up with the reduced rational equation of x plus 3 all over x minus 1. The factor that remains in my denominator is the factor that I use to find my vertical asymptote. So I set x minus 1 equal to 0, and I solve for x, and I get x is equal to a positive 1. Let's take a look at example 4. If I wanted to find my vertical asymptotes, I would have to factor my numerator and my denominator so I could simplify my rational equation. I would end up with f of x equals, and I would have to do MIF term on this one, so I'm going to do that off to the side. To do MIF term on this one, be careful, I would multiply my 3 times my negative 8, I would get a negative 24. I need two numbers that multiply to give me negative 24, but will subtract to give me a negative 10. I'm going to use a negative 12 and a positive 2. I'm going to divide by my leading coefficient. So I divide by 3, divide by 3. I reduce if possible. Negative 12 divided by 3 gives me a negative 4 over 1. 2 divided by 3 just stays 2/3. I put my x in my denominators, and I end up with the factors x minus 4 and 3x plus 2, all over x plus 4, x minus 4. Then I would look and see if there's anything that can be canceled or reduced away. I can get rid of my x minus 4s. My reduced rational equation would be 3x plus 2 all over x plus 4. The factor that remains is the factor that gives me my vertical asymptote. So I set it equal to 0. I get x plus 4 equals 0, and I solve for x. When I do that, I get x is equal to a negative 4. So I can see on my graph that x equals negative 4 if I were to draw a vertical line going straight through that negative 4, extending all the way up and extending all the way down. I can see that my vertical asymptote is right there. Thanks for watching. Now you know how to find vertical asymptotes when looking at rational equations.